Hello, this is Mr. Wandell, and welcome to the seventh video in the lecture series. This one's about climate and ecology, and we're really going to focus on how the climate plays a role in determining the ecology of an area. And so probably one of the first things I want to define is the difference between climate and weather. And it's kind of famously put by Mark Twain, climate is what we expect and weather is what we get. So weather would be kind of the daily physical conditions of the lower atmosphere, right? Is it raining? Is it hot? Is it snowing? Is the wind blowing? Those types of conditions. Where climate is kind of the average weather of at least 30 years period. So it's the weather averaged out over a long period of time. And if you look at the picture of the globe here, the satellite image of the globe, you can see some pretty similar areas, right? We've got a very desertous biome here, and we've got one also out here in the west. And there's a little bit of desert down here in South America, also down here on South Africa, and then Australia's got a very large desert in it as well. And something you may notice is that these desert locations are kind of happening at the same latitudes, right? If we drew a line all the way across here, we'd have about the same latitude for those deserts, and the same is true up here. All right, very interesting. What if we looked at, let's say, tropical rainforest, right? We've got the Amazon tropical rainforest here. We also have a tropical rainforest in Africa. And then over here in Indonesia is another tropical rainforest. And again, this is occurring at about the same latitude. And so climate is playing a role in the type of biome we see at these parts of the globe. And it's true for all over the globe. So one of the main driving factors here is the tilt of the Earth. And this image doesn't really do a great job showing the tilt of the Earth. But remember, Earth is on a axis, right? So here's the equator. I'll put an EQ here for equator. And we've got a tilted axis, right? It's not perfectly straight up and down. That tilt is 23.5 degrees of tilt. And so what happens is as the sun's rays come in to our atmosphere and then shine onto the surface of the Earth, due to the round sphere of the Earth and then the tilt, we end up with areas that have unequal solar heating, or they get an unequal amount of light. And so what this shows, right, we've got equivalent amount of solar radiation or solar energy between A and B here. And what happens due to this round surface, that same amount of light is spread out over a really large area here, so it's not very concentrated, right? Very spread out. And then down here on the equator, it hits a much smaller area, so that's a much higher concentrated atmosphere. And if you were an experienced traveler or familiar with geography, you would know that this is a very warm region, right? Because that solar power, the solar energy, the heat is very concentrated in a small area. Up here, it's going to be much cooler, right? And that cooler atmosphere is due to that spreading out of the solar energy. One thing that's good to remember here is that the pressures, air pressures and air temperatures are going to neutralize from the warm regions to the cold regions. This is a picture of the globe. We got a lot of drawings on here. I'll do my best to break it down and make it as simple as possible. I'm going to switch my color over to, we already have a red. Let's switch my color over to magenta. That'll be a good color we can see. So what we've got right here is the equator. The equator is going to be the area of the globe that gets the most direct sunlight or the most concentrated sunlight. So we would expect it to be the warmest. And what does warm air do? Well, at the equator, that warm air, and this is the warmest air on the planet, supposedly, that warm air is going to rise. So we see these cells, and these are called Hadley cells. We see that warm air rising up at the equator. As the warm air rises up into the atmosphere, it's going to start to cool down. And so you've got really warm air. Warm air is going to have a lot of evaporation happening. So it's going to be very moist air. There's going to be a lot of water evaporated in that air. As it cools down, it precipitates out. And so these little green lines here are showing rain. And we get a lot more rain at the equator because that warm, moist air is rising up. And as it rises, it cools and it has to precipitate out, right? Cold air can't hold as much water vapor in it as warm air. Once it rises up, it's kind of this conveyor belt action, right? In order to replace the air that's rising at the equator, it's got to come from somewhere else. It's going to get pulled from northern latitudes, or in the southern hemisphere, it get pulled from more southern latitudes. And so the rising air is then going to take its place, and we get kind of cool air falling on what's called here the desert belt. The reason why it's called the desert belt is this cool air has already precipitated out all of its moisture, or the majority of its moisture. And so because it's already precipitated out most of that moisture, there's very dry air that's coming down here at 30 degrees north or 30 degrees south. And that dry air is responsible for forming some of these deserts, right? Here's our Mexican and southwestern United States desert. Here's the Saharan desert over in Africa. And then you've got your desert down here at the bottom of South America on that 30 degrees south latitude. So it's very dry air. We also get another cycle up here. So in comparison, the air at 30 degrees is very warm compared to what's going on at 60 degrees, right? This is going to be the North Pole up here. So it's very cold air. And that warm air is going to move northward as it rises, right? Because it's kind of being pushed out by that cold air. It's got to go somewhere. And it's going, part of it's going south, part of it's going north. As it gets pushed out, it's going to be forced up again. And as that relatively warm air rises, again, it's going to precipitate out. So you end up having a lot of forests or precipitation up here at 60 degrees, right? And most of Canada is covered in forests. Forests need the water, and they get it from this rising air mass. And so really important to take away here is that these are called Hadley cells here. This is a Hadley cell. These happen between 30 degrees north and the equator, or 30 degrees south and the equator. They are responsible for heavy precipitation at the equator, and they're driven due to that unequal heating, right? This is the warmest air. It's getting the sharpest angle, or the most concentration of solar energy. This is much lower concentration in comparison. Another thing that we see here is that these kind of global wind patterns are curved, all right? If the globe was standing still, what you would see is you would see that cooler air from 30 degrees going straight down to the equator, where it would rise and then cycle back, right? And you'd have this kind of stationary little Hadley cell. But because air is not connected to the surface of the Earth is actually spinning underneath these Hadley cells. And this is an effect called the Coriolis effect. The Coriolis effect simply means that the Earth can rotate underneath a projectile, or it could rotate underneath air molecules or water molecules. So the Coriolis effect plays an effect in how water currents move in the ocean and how air currents move on land. What happens if we had this giant cannon that was capable of firing a shot all the way to the North Pole? While the cannonball is in the air, the Earth is going to spin, right? It spins east to west. So we picture the globe spinning beneath the cannon shot. Your cannon would not land up here on the North Pole. In fact, the cannonball would land somewhere out here in Russia, because as the cannon is traveling, that Earth is rotating underneath the cannonball. The same is true for airplane flights, right? If you're flying in the northern hemisphere and you're leaving, let's say you're leaving from the Ivory Coast over here, trying to fly up to England, right? And you try to just fly straight north, you're not going to end up in England. You're going to end up somewhere in Eastern Europe. So those paths are actually having to accommodate for the curve of the Earth. You might make a path where you are heading a little west and letting the globe spin underneath you. In the southern hemisphere, it's reversed. So instead of turning off to the right like it does in the northern hemisphere, in the southern hemisphere, it would turn out to the left. And again, the same reason, because the Earth is spinning east to west. Right, that shot's not going to land at the South Pole. It's going to land a little bit off to the left of it, if you flip your perspective. This also affects the ocean currents. So these really large ocean currents are called gyres, and it's just kind of how these major currents move throughout the ocean. And if you look in the northern hemisphere, right, here's our equator right across the middle. In the northern hemisphere, we get a rightward spin to our gyre, and that's due to the Coriolis effect, right? Anything leaving from the equator due to the Coriolis is going to veer off to the right, and so these currents all veer off to the right. In the southern hemisphere, everything's going to veer off to the left, right? And so we get these leftward spinning currents. These currents are also really important for distributing temperatures and nutrients throughout the oceans, and we'll kind of talk about that later. But if you see from the equator where that warm water goes, you end up with warmer climate, right? It's warmer in New York than some places over here in Europe because we're getting that fresh warm water to kind of control the air temperature as it rises north. But that's essentially video 7. Please come to class tomorrow with some sort of notes and be prepared to discuss video 7. Thank you for watching.